All right, so let's get started with this warm-up here. So we have 4 integrals, and the first question isn't go ahead and do these by substitution, it's should we even use substitution? So yesterday we kind of reminded ourselves all these things about the integral, the definition, the fundamental theorem, all this stuff. But as far as actually doing integrals, we only have a couple techniques so far. One, is it a basic integral? Can we integrate x squared or something like a power, or maybe a trig function, or one of these kind of defined integrals that we have? And 2, can we use the properties? The integral of a sum is the sum of the integrals, those properties. And then maybe the third one would be substitution. But we don't have any other techniques. Now, as we get into chapter 7, we're going to start learning more techniques: integration by parts, partial fractions, trig substitution, these other ones. And so a big idea is going to be not necessarily just knowing the technique, but knowing when to apply the right technique. That's where we're going to start off asking questions like that right now. So to use substitution, I'm looking for a function, an inside function. I'll use inside loosely. It's the inside of a composition of functions whose derivative is a factor. So for the first one, is this something I can use substitution on? Okay, so I see some nods. If yes, then what's u? If yes, then what is my u function here? U equal to what? 1 plus x squared, absolutely. I see that function. It looks like the argument of some other function, the 1 over x squared function. And the derivative of this is going to look something like x. It's going to be 2x, but it's going to look like a factor times x. And there's my factor. So the derivative is a factor in this integrand. So once I see that, I can identify u. Then I can take the derivative of u. In this case, I'll get 2x. I'm going to solve that thing for dx. I will get 1 over 2x du equals dx. You might have been taught other ways to do this, so you might not necessarily be solving for dx. Some people would leave the x on the right-hand side and replace x dx with that. That's totally fine to do. I'm going to just do it this way. It's very systematic and less thinking involved, maybe more mechanical. Whatever your preference is. So I have these values. No, I have my u. I have dx defined. I'm just going to plug these values in. This changes my difficult integral into an easier integral, where I have x over u squared instead of all that stuff squared. I replace the dx by what it's equal to, which is 1 over 2x du. I'm very happy because my x's cancel out. If they don't, I would have a problem. And I'm really left with 1/2 times 1 over u squared, which I'm going to write as u to the negative 2 power du. I write it as u to the negative 2 just because I can see the power rule a little easier that way. Right? Just a notational adjustment to help me see the power rule a little easier. And from here I do the integration. Now 1/2 can sit out front. I'm really integrating u to the negative 2 power, so I can use the power rule directly. So this is u to the negative 1 divided by negative 1. I'm left with negative 1/2 1 over u, plus c, of course. But at this point, I'm not quite done yet. What's the next step here? I've done the integration. I've integrated this easier integral. What's my last step? Substitute back in. I started with x's. I want to end with x's. So I will substitute back in to get negative 1 over 2 times 1 plus x squared, plus my constant. Any questions? Anybody confirm the result? So people got? Now, if I wasn't sure, how would I check my work? I always take the derivative. If I take the derivative, I should get back to this integrand piece. Or I can use my calculator or Mathematica. Right? Use your resources here to check your work. There's nothing that frustrates me more when I give an exam and people leave a half hour early and they're not checking their work with their calculator. Right? That's what it's there for, is to clean up our mistakes when we make little math addition errors and other errors. So make sure you're in the habit of checking your work. All right, that's the first one. Any questions about that first one? Remember, if you miss any of those little steps, please ask. sure you get your questions answered. All right, going to the second one. Is this a candidate for substitution? You got an x squared and x, isn't the derivative of x squared something like x? Doesn't that work? Can I use u equals x squared? I can't. Because the derivative of x squared is something like x, but x isn't a factor here. Sine of x is a factor, right? So I don't see a function whose derivative is a factor. I see x squared sine x. The derivative of sine x is cosine. I don't see any cosines around. The derivative of x squared is 2x. I don't see any x's hanging around. Okay, so that's not a candidate for substitution. What about the next one? This one is a candidate, right? I have x squared as my inside function, and the derivative is x, which is a factor, 2x. But once again, I don't care about those multiple differences. So substitution is a candidate. I'm going to let u equal x squared. I'm going to follow that process again. The derivative is equal to 2x. I'm going to solve it for dx. I'm going to plug in my values. X sine of u, 1 over 2x dx. My x's cancel. Looks like I have 1/2 integral of sine of u du. Oops, this should be du here. So I've taken a hard integral and turned it into the integral of sine. Integral of sine should be, let's see, negative cosine. And lastly, I replace my u's by what they're equal to. And add my plus c. I'm going to confirm that one. How does that one look? Once again, I'm going to go through these pretty fast because I'm hoping people got in here early and have kind of put the work in and they're just confirming the results of my work. On the last one, is this one a candidate for substitution? I see some yeses, some no's. If it is, what would I try for my u? Seems like I have a couple options, right? It seems like I have, well, the derivative of 2 plus cosine should give me something like sine. Well, the derivative of sine should give me something like cosine. Can I use either of them? Turns out I can't. The derivative of sine is cosine, but cosine is not a factor here. 1 over something plus cosine is a factor, and that's different. In this case, I couldn't use this u equals sine. However, if I use this one, well, sine is a factor. It's a factor of this integrand. So I can use u equals 2 plus cosine of x. In fact, I could just use u equals cosine of x. By using 2 plus cosine of x will make my next integral even easier. So it will just kind of disappear anyway. So I let that be my u. I take the derivative. I get negative sine of x. I solve it for dx, just following these same steps. Plug all that stuff in. I get sine of x over u. I replace the dx by what it's equal to. I use parentheses because if I don't, I will forget and think that's subtraction in the next line. Right, so I use that to make sure I don't mess that up. I'm happy because my x terms all disappear. I'm really just left with negative the integral of 1 over u du. And what is the integral of 1 over u? Almost. Natural log of the absolute value. And lastly, I put in my u stuff. And I'm not sure about this publisher. I would assume they're the same, but Wiley Plus for sure. They want your absolute value signs in there. I would assume this is the same because it really is an important piece. All right, so any questions about that last one? Yep. It's kind of by definition. And we say the integral of 1 over u is equal to the natural log of the absolute value of u. Okay. As a justification of why, we can think of the natural log. So here's a picture of e to the x. Looks like that. Natural log is actually the inverse of e to the x, so the natural log should look like this. But that thing actually never hits 0. It's like e to the x never actually hits 0. That means natural log doesn't actually hit 0. So if I plug in negative values and try to get the result for natural log of negative 2, that thing doesn't exist over here. But if I think of what 1 over x or 1 over u would be, oops. Come on. 1 over u should look like this. And so when I integrate 1 over u, even if I'm integrating it from these negative values, there's really a function over there, which means there really is an area under this curve that I should get a value for my definite integral. So if I just had this being natural log of u, when I use the fundamental theorem and I started evaluating at the endpoints, I would be getting natural log of negative something and negative something, right, which say is undefined. But it really is something that should be defined. So it's kind of like we throw in the absolute values to account for that, because we know there is a symmetry. Okay? So you could say it's part of the definition of that integral, and we've shown that to be true, but this kind of visual thing might help a little to justify why it's important. Good question. Other questions? All right, so now we're going to move on to 6.1. All right, so 6.1 is about position, velocity, displacement, all this kind of stuff. So from the reading, we kind of should have a definition of some of the basic stuff here. So for instance, we saw that if we have some function s of t that represents an object's position along a line at some time t, I'll say in hours, then what does some of this stuff mean here? What does s of 0 represent? If s gives me the position of an object at some time t, then s of 0 is position at time equals 0. And we're going to call this our initial position. We're keeping track of time. We have our stopwatch. When we start that thing, this is where we're at, s of 0, when time equals 0. S of 2 minus s of 0, what would that represent?
Change in distance over the first 2 seconds.
Absolutely. I'll call that the displacement. Displacement after the first 2 hours. That's the difference between where I am and where I started. And next we want to talk about velocity. Well, velocity is just, well, it's kind of like the change of position over the change of time. Sort of. That would give us an approximation for velocity, right? Maybe an average velocity. And if we said that we moved 3 miles in 2 hours, we'd have some sort of average velocity. So we want to be more precise here to find an instantaneous velocity. Well, we take smaller and smaller time steps. We would look at the limit as that change in time went to 0 of this thing. That would essentially give us the derivative of position with respect to time. And that would give us our instantaneous velocity. And most of that stuff should be a review either from this section or from Calculus 1. Velocity is the derivative of position. But now as we're reviewing our integration stuff, and we have our idea what the fundamental theorem says, now we can see that the fundamental theorem of calculus would say that the integral of velocity with respect to time over some time interval from t equals a to t equals b, well, if velocity is just the derivative of position, I really have this thing. And then by the fundamental theorem, what would this thing equal? Is it? Absolutely. So it's the position at time B minus the position at time A. It's the displacement over that time interval. Right? This is essentially derivative of capital F. Right? So S is our antiderivative. It's a thing where the derivative gets me the integrand. So this is really just an application of our fundamental theorem. And so that tells us if we integrate our velocity, we get the change in position. If we integrate the derivative of position, we get the total change of position. So let's just make this a little more familiar here. We're going to talk about the same idea about 3 different ways here. So Marquette, say about 100 miles away-ish, I think. It takes me 2 hours to drive to Marquette. How fast am I driving? $100 miles, 2 hours, 50 miles per hour, right? 50 miles per hour. And how'd you figure that out? Divided by half, right? We're using an equation here. We have the rate is equal to the distance divided by the time. So we got 50 miles per hour. So, do I drive like a grandpa? No. I mean, you might think that looking at 2 hours, right? But no, I'm not really driving 50 miles an hour all the way to Marquette. That's not my instantaneous velocity. That's not what my speedometer is saying. That's the average velocity. But of course, I'm not driving 50 as I leave Houghton. Does that make me a grandpa? I don't know. That's safe, right? When we go through other towns, I slow down to the proper speed limits. So this is just the average. It means sometimes I'm driving slower, sometimes I'm driving faster. So how do I go about finding my real speedometer reading? If I want to find what my speedometer is saying, I have to look at much smaller time intervals. This is an approximation to how fast I'm driving. It takes the whole distance divided by the whole time to give me this average velocity. But if I want to say, well, wait a second, let's just drive for 1 minute and see how far I go. Let's just drive for 1 second and see how far I go. The smaller that time chunk I look at, I'm really looking at now the limit as I change my distance and I change my time, and that's going to give me that derivative. That's going to give me that instantaneous velocity idea. So far, so good. So I really don't drive 50 miles an hour the whole way there. In fact, my velocity might look something more like that here. Call that the 2 hour mark. Maybe this is a plot of my velocity as a function of time. This is my time. So it's not constant. Now, just like we can do this to get maybe an approximation for the instantaneous velocity, the derivative, we could do the same thing. If I was driving 50 miles per hour and I drove for 2 hours, you would expect me to travel a distance of 100 miles, right? All we're doing is flipping this equation around. We're just saying that distance is equal to the rate times the time. But the same problem applies. It's not very likely that I am traveling exactly 50 miles per hour for that whole thing. So if my velocity is really changing, how then do I approximate how far I've traveled? I can kind of look at this picture here. I mean, this isn't just some fixed velocity, so I can't just take that velocity times that time. Instead, my velocity is changing. It makes it harder for me to approximate my actual distance traveled. So what do I do? Absolutely, that will give me the right answer here. Along the same lines I was talking about with the derivative here, I look at a smaller timestamp. It's the same thing here. I'm going to look at a smaller timestamp. I'm going to say I might not be able to approximate this whole thing, but if I looked at a little tiny piece, just a little tiny piece, the idea is that the velocity isn't changing very much over this small little timestamp. right? The velocity is pretty different across this whole thing. I have a velocity of 0. I have a velocity of whatever this number is. Maybe it's 80 miles per hour or something, right? Yeah, not a graph anymore, right? But the velocity changes a lot through this interval. But if I look at it as a small enough little timestamp, now the velocity really isn't changing very much. It's, 51 here, it's 52 here. It's not that big of a change. So over this little time interval, I can approximate the actual distance pretty easily. I take whatever the velocity is, which is a pretty good approximation. It's pretty much the same everywhere through this interval. I take that velocity times the time, and that should give me the distance I traveled in this little time step. And then I just do that for all those little time chunks. And once again, if I think about what this is telling me, this is the velocity now times that little change in time. It really is giving me, just like you said, the area in that little rectangle. And if I add up all those little distances, it's giving me all those areas. It's giving me the area under the curve. Okay? But the philosophy is the same here. I have a big problem. I don't know how to do it. I can maybe approximate it, but not very well. If I want to improve that approximation, I'm going to look at a smaller chunk, a smaller slice, smaller timestamp. Okay? So what I can do here is take that's the approximate distance in one little time interval. Then I want to take those and I want to add them all up. That's me adding up all those different timestamps. I say that's a pretty good approximation to the total distance. I don't want a pretty good approximation. I want the exact distance. So now what I'm going to do is take a limit. I'll take the limit as delta t goes to 0. And then I will look at my expression and say, wait a second, I know what that is. I have a definition for that thing. That thing, by definition, is the integral of velocity with respect to t over that time interval. Now, a lot of you could probably have jumped to that right from the very beginning. But that process is going to be important. That constructing these small little chunks, adding them all up, taking a limit, and recognizing that as the integral is really the process in general. Okay, a couple other kind of related questions then. Now that's supposed to give me the total distance I've traveled. Let's see, what about this one? What's the distance I've traveled? 0. That doesn't make any sense, right? I'm clearly traveling. I clearly have some velocity at some different points. My car is driving. I've driven some distance. Right? We are not driving in reverse to reset the odometer here. So I should expect to have some positive distance when I've traveled here. So the idea is that what we did before is we were really finding the displacement. Right? When I went like this and this, and I did an integral, it was adding up all those distances I've traveled, giving me the total displacement. But over here, my displacement is 0. I traveled some distance here. If I this integral to find the distance I traveled, I got to here, I stopped, I have a velocity of 0, and then I had a negative velocity. Well, velocity has a direction component, exactly. So I'm going backwards. I got halfway to Marquette, I turned around, and now I'm coming back. And then I got back to Houghton. So my displacement is 0, but clearly I've traveled some distance. If I actually want to calculate that distance, what are my options here?
Absolute value underneath the x-axis.
Absolutely. So instead of integrating the velocity, I could integrate the absolute value of the velocity. The absolute value of the velocity really gives me the speed at which I'm traveling. So in MATLAB, velocity and speed are a little bit different. Velocity has a direction component, whereas speed doesn't. Okay? All right. The last question I have about that, so far we have that the total displacement, sorry about my poor handwriting here, displacement, is the integral of the velocity vector to whatever our time interval is. Our total distance we're traveling, well, that is integrating the speed, the absolute value of the velocity over that time interval. And the last thing I want to figure out is my current position. right? Or your book's going to call it future position. It's where am I, say, here. Where am I? Now it's a little tricky to find that out. I mean, I could integrate from here to here. It's all positive here, so that would give me the distance I've traveled. Will that give me my position? Sort of. If we're building off our exact example here, where we are starting in Houghton, that's fine. But all I have when I go from here to here to get this distance is you've traveled 20 miles. Well, it definitely depends on where you start at. Right? Your current position depends on where you start at. So if I look at what I had before, I had this thing as my integral. And if I tweak that a little bit to say the integral from 0 to some value, the result would be s of b minus s of 0. And it says that the displacement is going to be your final position minus your initial position. What I'm asking you, my current position, my future position, is really just this value. So all I have to do is take this and solve it for this value. So if I just add my initial position over, kind of makes sense. Take your initial position plus your displacement, and that should be where you're currently at. So all we're doing here for current position is just taking our initial position plus the integral from 0, to whatever we want to call that thing. Like that. Okay, any questions about that? All right, all this stuff is really just coming from a very simple equation. It's coming from distance equals rate times time. And so I want to paint kind of a general description of how we're taking this equation to generate these things. It's a process we're going to repeat a lot as we model with calculus. It's really the power of calculus. This is really what we do here. We have some problem and we want to approximate it. We can't find this big problem all at once, whether it's finding the distance or finding the rate or finding the mass of some object or finding the amount of oil that's leaked out of a tanker, as we'll see a little bit later. We have some big problem and it's complicated. We can't really do it with some simple algebra. So what we do instead is we approximate it, like we did with our distance equals rate times time problem. We said, okay, rate is approximately the change in position over the change in time for some little changes. And we use that to generate an equation. So for instance, if I want to find that change in position, if I had some function, I'll say, I might take the function at some later value minus the function at some current value and divide by the total interval length. And that would be a good approximation for this rate. And that formula is for the average velocity, if you will, the average rate of change. So I use that idea to improve my approximation. But then the last step is to perfect my approximation. I'm going to take that and I'm going to use the limit idea to generate a perfect answer here. So for instance, in this case, we could look at the limit as b approaches a of this thing. And if we did that, that gives us, by definition, the derivative. And that's just another definition of the derivative. And we do that exact same thing with the integral. We're trying to approximate distance, so we start out with that rough approximation. Rate times some change of time. And we generate an approximation. We do a left-hand sum or a right-hand sum. So we'll add up a bunch of little pieces here. All right, we'll divide it into 4 intervals and we'll find our function value at the first one times some little time step plus our use t's here. Plus our function evaluate the next one times that little time step, so on and so forth. And we'll get an approximate result. Right, we'll add all these things up to get the sum. As we work towards an exact answer, we're going to take the limit of that thing. So finally we apply our limit to get an exact answer. And we define that thing to be the integral. So once again here, not the details of this chart that are important, it's that process of approximating something big, seeing how we can chop it up to improve that, and finally taking the limit to perfect it, and that generates our derivative or our integral. Now in the specific problem we're working with, when we're talking about integrals, it doesn't have to be distance equals rate times time. Now, if we looked at that, we were integrating the change in position with respect to time with respect to t, from A to B. I can almost do a little bit of cheater math here, right? I can almost be like, hack them like they're fractions or something. In which case I'd be integrating ds. Integral ds is just s evaluated at the endpoints. It kind of gives me that thing. But it doesn't matter whether this is ds, dt, or position versus time, or d capital P with respect to time, population change with respect to time. The fact is I'm integrating a rate of change. And that process of integration, as we saw from the fundamental theorem, is kind of undoing the derivative. So the big idea from this section is that when we integrate a rate of change, the result is the total amount of change. And so in section 6.1, your book kind of goes through both of these cases. It does a specific thing with distance and velocity, and does the generalization. So if we can generalize all this stuff to any rate of change, all of our little ideas along the way should be able to be generalized. What's an initial position? What's a displacement? All that will be in terms of whatever the rate of change that we're given is. So for example, oil is leaking from a ruptured tanker. No! And this was a real problem, obviously. Now they're measuring the flow rate outside of this hole. Right? That's something they can actually measure. So they find out that the rate of the leakage is given by this equation, 50 times e to the negative 0.02 times t. That many thousands of liters per minute. And so I'm going to let A of t be the name for the amount of oil that is leaked out after t minutes. I'm just giving that a name. So I have a rate of change and an amount, rate of oil leaking and the amount of oil leaking. And so let's ask those questions. What does A sub 0 represent? We use t as the time the rupture occurred, and then A of 0 would be amount of oil at time equals 0. So that could be a couple things. We could say that's the time of the oil leakage, in which case that value would be 0, because 0 oil has leaked when it first ruptured. Or we could say that t equals 0 is when we found the leak. Right? And there could be some amount that is already leaked, in which case A of 0 would be whatever that initial amount of leakage is. Okay? And that's something we choose. We choose how we're going to define our time parameter here. Yep?
Is that the prime symbol over the R?
Nope, I'm sorry, that's it. It's a vector symbol for some reason here. We're going to remove that. Okay. Other question? All right, so this is the initial amount of oil. Amount of oil that has leaked. So once again, we could define t in different ways, and it will change the actual value here. point here is to think about what it could be. So what does a of 60 minus a of 0 represent?
Or oil leaked after 60 minutes.
Absolutely, the amount of oil that's leaked after 60 minutes. Once again, that will vary a little bit depending on how we define a of 0. That could mean how much more oil has leaked out the first hour after we found this oil leak. Or if we define t equals 0 as the time of the original incident, it could mean the total amount leaked, period. Okay, so both those definitions will be valid here. Well, let's calculate this thing. How do we actually calculate how much oil has leaked in the first 60 minutes here? Absolutely. We're going to integrate r of t, not a vector, r of t, with respect to time from t equals 0 to t equals 60. And this is something we can really do here. We can integrate from 0 to 60, 50 times e to the negative 0.02 t dt, and find that value. All right, then we don't actually need to calculate here. Once again, it's the setup that's important. Seeing that integrals aren't just area under the curve. They are very broad, any kind of big problem. You can see this is a challenging problem, right? Because as we see here, the amount of flow is changing. And that makes sense. You have a big tanker, it's full, it leaks, oil is shooting out, right? As it starts to empty a little bit, the flow rate will get a little smaller. So that rate of change is fluctuating. So it's hard for us to count exactly how much oil is flowing out. Right, but if we can generate that equation, which maybe we can monitor by putting something at the source, kind of measuring the flow rate, we can actually keep track of how much is flowing out. All right. Any questions about this problem? Now, there's one other problem I want to do from this first section. I'm going to go through it kind of quickly because really it's example number 4 from the text. And the reason I want to talk about it isn't so much because I want to do it, because they give you the solution in example 4, because I want to talk about how to generalize it. Okay. So this is, can you guys see that in the back? I'm going to have to make some bigger text now. Not really? Okay. That better? Everybody see that? Okay. If you ever can't see anything, just ask and I'll adjust it. Okay, so we have an artillery shell, which is fired directly upward with some initial velocity. So we're shooting the shell in the air. It's going to be a projectile in motion. How many people had a physics course before? Talk about projectiles in motion. Okay, so. All right, so in physics class, you learn a bunch of equations for how this projectile flows once it's been launched. Because once it's been launched, the only force acting upon it, if we ignore wind resistance and some other things, is really gravity. So it says that this thing is fired directly upward with some initial velocity from some point 30 meters above the ground. Assume the only force of gravity acts on the shell and it produces an acceleration of 9.8 meters per second squared. Find the velocity of the shell for t greater than or equal to 0. So we're basically told the acceleration is 9.8 meters per second squared. Depends on what we count as up or down. Yeah, so we'll count this as negative. Yep, absolutely, right, because it's opposite our direction of motion. All right, so that's our acceleration. But acceleration is just the derivative of velocity with respect to time. So we can integrate our acceleration with respect to time from 0 to some later time. I'm going to call it t2. And on the one hand, our acceleration, which is the derivative of velocity with respect to time, should give us the velocity at t2 minus the velocity at time 0. But on the other hand, it's really just integrating negative 9.8 with respect to t, which in this case would give us negative 9.8 t evaluated from 0 to t2, which would give us negative 9.8 t2. That's doing the integration and evaluating the endpoints using the fundamental theorem. So what is our velocity at some later time? Well, I just solve it for that thing. I add the initial velocity to the other side, and I get this thing. And we know that initial velocity because they give it to us. Well, let's generalize it. Let's say, what if initially we just had some initial value, call it v sub naught. Then this would just be v sub naught. And then later, if I want to find the position at some later time, well, position is just the derivative of velocity. So if I want, I could integrate the velocity with respect to time from 0 to some later time. On the one hand, I should get the change of position. And on the other hand, I'm just integrating negative 9.8 t plus some v sub naught. But when I do that integration, I'll get negative 9.8 over 2t squared plus v sub naught t. Like that. And once again, all evaluated from 0 to t2. So all that does is give me t2s here and here. And if I solve that for the position, I get negative 9.8 over 2 t2 squared plus v sub naught t2 plus some initial position. I'll call it x sub naught. I'm calling it x sub naught because this is the formula you have in physics land. So we could use the actual values they give us in the problem, but all they do in physics is say, let's just leave these things as parameters, as things we can plug into a formula later. They just do some basic integration, given the acceleration, and they generate these formulas. If you had physics in high school, these are the formulas you probably had to memorize for some tests. Like these are the equations of motion. And so all those things are just generated from some integration here. Any questions about that? All right. So the next topic is 6.2. Regions between curves. Okay, so I have some shaded regions here. We know from Calc 1 that if I want to find the area in the curve, I just integrate the function over the interval. So this first area is just the integral from a to b of f of x dx. That will give me that first area. And now we want to make sure that we understand how to find this other region. And we're kind of going to generate it two ways. One, we want to, once again, emphasize the process here. We got this integral on the left by breaking our big region into smaller regions, finding the area of that rectangle, and adding them all up. So we'll do the same thing on the right region. I'm just going to generate a small rectangle and find the area of that rectangle. I'm going to call that a little change in the area, delta area. And all it is the height and width of that box. Well, the height of that box is going to be this distance minus this distance. It's going to be the distance to the top curve minus the distance to the bottom curve. That should give me the height of the box. The width of the box, what's the width of my box? Should I use the width of my box here? I could if I was chopping it to n intervals, right? I would be talking about b minus a. So I could take b minus a divided by some n and find a little interval, right? That's what I'm going to call delta x, some little change in x value. So the idea is I can't find the area all at once. I don't have a formula for the area of squiggly shape. I don't have that formula. So instead, I'm going to look at a small enough slice, where if I look at that small enough slice, it's really just flat on top. If I could cut this small enough, it's practically flat on top and on bottom. Which means my shape turns into a rectangle, which is great because I have a formula for area of rectangle. Height times the base here. So I generated a formula for my height, and this base is just going to be some small change in the x value. Right? It has to be small, otherwise the top and the bottom won't really be that straight. But if it is small, like a small delta x like that, that should be a good approximation for that area there. But I don't want just that little piece of area, I want all the area. So I could say an approximation for the total area would be adding up all those slices. But I don't want an approximation, I want the exact value. My value gets better if I take smaller and smaller slices. So what do I want to do to make this a perfect area? Should I do? I'll take the limit. I'll take the limit of this thing. And that will turn this into an exact answer. And then I recognize this thing. This thing, by definition, is the integral. It's the integral f of x minus g of x dx. And that should represent the exact area of this region. So it's just the integral of f of x minus g of x dx from a to b.
Are we going to have to explain all that? Or?
Nope. You can absolutely just jump to the integral and do the integration. Right? In fact, I'm going to say this stuff so many times it's going to drive you nuts. Right? But I'm going to say this pretty much every time for any one of these modeling problems, because that's really the core concept. When you get to your engineering classes and you're modeling, you're going to be given these kind of problems. Like where I have something to figure out, I don't know how to do it. Well, let's break it down into pieces. And you're going to have to generate the integral, not from some formula, but from the nature of the problem. So that's why I want to emphasize that. But no, you absolutely don't have to write the sum or the limit of the sum or any of that kind of stuff. All right, now does it change if we do this one? Is that any different? Do I have to modify my formula at all?
You're adding g of x.
So suggestion is this. It's tempting, right?
No,
And that's the
because
first thing you want to do, but
if you have a negative and a negative, it changes to a positive.
absolutely. You do not change your formula. You just keep doing this. Because if we look at some specific spot, well, if I went up here, let's give it a number. Let's call this thing f of xi is, we'll call it 3. Looks like a 3 to me. We'll go down here. This is g of x1. What would be a reasonable value for this one? Would be negative 2? Certainly negative, though. And so if I add those, I'm going to get a value of 1. But if I subtract them, I will get a value of 5, which is really what I expect here. The distance between this 5. So we find the distance between two things, we're always subtracting. We're not adjusting for whether it's above the x or not. So this is still the formula for the area between these two functions. Practice. All right, your turn to practice here. I want to find the area of both of these shaded regions. The yellow and the, I don't know what color that is, light blue. See if you can set up these integrals. You don't have to actually have to do the integration, but see if you can set up the integrals to give me both of these areas. It's stuck. Ask the neighbor to talk about it. Feel free to work in groups on this. but not all the way.
See if we do this point and then this point over this point.
All right. Getting there. A little bit of a start, or a little bit of talking at the end here. Feel free to talk. Work about these in your little groups here, because, yeah, the worst thing you do is just kind of stare at it, right? And then we're not. It's easy to stare at a problem. I don't want that same thing to happen on the exam, where we're just kind of like, I know I'm supposed to do something, but I've got to do we have to find a way to kickstart ourselves. So I'm going to do the yellow one first. Maybe I don't know how to do this problem. Maybe I'm totally stuck. Draw the picture. And say, okay, I'm going to draw this little area piece. That's one little representative area. If I can find the area of that thing, I can just add them all up and do the integration here. So what is the area of that slice? Well, it's going to be this thing minus this thing. But I don't have this solved for y yet, so it's not really giving me the height yet. So I'm going to take that and solve it for y. It's going to give me the square root of 1 minus x squared. You tell me the x value, that gives me the height. That gives me this distance. So I take that distance minus this distance. All right, so minus x squared, that should give me the height. Now what's the thickness of this? Well, it's this little tiny change of x value. All right, so it would be the delta x. That should give me the area of that rectangle. Now I want to add them all up. I want to make it exact by taking a limit. Hooray! It's the integral of 1 minus x squared dx. Now the hard part. From where to where? From 0 up to what I'm going to call A is the intersection there. I don't know what that is. I got to figure that out. And that's not necessarily an easy thing. Right, but that's just one small part of this bigger problem. Now to find that intersection, I'm going to set those two equations equal to each other. The first one says y equals x squared. The second one says y equals the square root of 1 minus x squared. So if that point is on both of those, it's got to satisfy both of them. All right, so now I got to solve that thing for x. I'm going to square both sides to get this thing. Add x squared minus 1, I get all this stuff. If I'm stuck there, I'm more than welcome to put that in your calculator and find the roots for this thing. I would let u equal x squared and just turn it into this, so that makes me happier. I can't see how that factors, so I'm going to have to put that into the quadratic formula. Turns out there's 4 roots to the original thing. 2 are going to be complex, 2 are going to be real, and we'll just chug through the math. It's a little bit tedious, but it's not too bad. All stuff we should be able to do at this point. Okay? When all is said and done, I'm really going to only have one candidate, though, because 2 are going to be complex, and I'm going to have a positive and a negative, and I want the positive x value. So I'll get some number, whatever it is, and then I'll be able to integrate from 0 to that number to find this area of the yellow piece. Okay? So it's a little trickier, right? It's not just f of x minus g of x. Now what about the other piece? This one looks easier, right? I'm just integrating from the axis to the function, so I'm just integrating the function. Once again, I got to find out that a piece, because I can't integrate all the way across. I have to integrate from 0 over here to find the area under this function, but then I switch functions. Then the ceiling isn't x squared anymore. Now the ceiling becomes the other function. So I integrate from 0 to a, this function, and I add the integral from a over to, what's this value over here? 1, absolutely, because it's a circle of radius 1. So I integrate from a over to 1, integral of this piece. So this is kind of a standard problem for this area between regions. So there's a bunch of these from the homework. Go through them. The idea is you might have to solve for those intersection points. You might have to break big regions down into smaller regions. And something else is going to be useful is instead of slicing vertically like this, we're going to have to talk about slicing horizontally like this. And to do that, all we're going to do is switch our x's and y's. Right? Y equals x squared. Y equals x squared says go to some x value and I will tell you what the y value is. But if I just solve this and say the square root of y equals x, this says go to some y value, and I'll give you the x value. So in other words, this distance here, that x value that gives me the distance, I can now solve for that and find out it's the square root of y. All right, so if I take these equations and solve them for the other variables, it will give me these horizontal distances instead of the vertical, which means this slice is now the square root of 1 minus y squared minus the square root of y. The thickness now becomes dy, and I integrate over some range of y values. Okay, and we're definitely going to practice more of that next time. Also for next time, start reading 6.3 and 6.4. We'll finish up this stuff. I'll answer any questions you guys have from the homework now that you're into the homework systems, and we'll go from there. And I have office hours right now.
I had a question.
Yep.
I have some time on exams and stuff.
Okay.
How do I do that over the summer? Do I still go to the office?
Yep. Just go down there, they'll give me a note and everything, and then, for example, let's make arrangements. If you have something before class or after class, we can start you early, start you late. And then I don't know if it's also a quiet environment, so the movie if we get to let's go with that. Okay. The trickier thing will be for quizzes. So
Quizzes are normally just in class.
okay.
Really.
Okay.
I'm not really pretty good with those.
Okay.
Just exams when it's like a longer thing. And
Okay. I'll just keep an eye on quizzes too, and then I'll kind of use you to gauge my time. So. Okay.
Does the structure get up like this in the fall too? For the recovery and everything?
What's that?
Are they going to do this kind of structure in the fall? Or?
No.